the frame we have attached with rigid body is called the body frame. Now, this body frame is rotating along with the rigid body, and of course, there is a space frame, space set of axis which is fixed in space. We have discussed it numerous times, and whatever equations we have written it in respect to body frame, because typically the convention is we take the body set of axis or body frame to coincide with the principal axis system of that particular object or particular rigid body in question. Now, if this happens, then the equations greatly reduces it in complexity, all the cross terms, all the products of inertia term vanish, and we have a equation which is very nice looking, we call it Euler's equations. But then there are problems. For example, if we try to gain the insight of motion with respect to the space set of axes which are the inertial frames, then we have a serious problem, because what we get in the Euler's equation, what we have is essentially three equations in terms of omega 1, omega 2 and omega 3, three differential equations. Even if we know the functional form of torque or we know everything about the system, integrating this omega 1, integrating these equations will give us omega 1, omega 2 and omega 3, which once again are represented in body set of axis. And if you understand the situation, we have a rigid body, let us say, okay, so this bottle is our rigid body. This is this is executing some kind of a rotation about some arbitrary axis with one point fixed. Let us say the fixed point is at the center and the arbitrary axis of rotation is in this direction, and so it is moving like this. And if I resolve this, okay, so now if I write the equation in body set of axis, so this equations will give us something which is the angular velocities which are again expressed in body set of axis, and it is rotating along with the rigid body. So, makes no sense. I mean it makes sense, but integrating those equations will not provide us what we are looking for. We are looking for example, angular velocity. Okay. So, we need to have some ways of connecting the space set of axis with the body set of axis. Okay. So, if we can, and if you recall, in the preliminary discussion of rigid dynamics, we came up with the conclusion that the degree of freedom of a rigid body is 6. Out of that, moment we fix one point in the body, we take out 3 degrees of freedom. So, we are left with 3 degrees of freedom of a system, and this 3 degrees of freedom can be 3 coordinates. So far, if you understand, in this entire discussion, we have written omega 1, omega 2, omega 3, but we never tried to express these omegas in terms of change in some angle. Typically, omega is some theta dot, theta being some arbitrary angle. We never tried that. Now, it is time we try that. So, we have 2 things to do. First of all, we have to express omegas in terms of some angle, number 1, and number 2 is we have to get a set of coordinates that connects the body set of axis along with the space set of axis, and which are measurable. So essentially measuring the change in these angles, we can talk about, we can describe the system in sitting at the space set of axis, which is the inertial frame of reference. Now, these angles, these are called the Euler angles or Euler angles. Okay. Now, there are alternative definitions available, many definitions available for Euler angles. We will stick to one particular definition. Let us describe what are these Euler angles. Let us assume that we have at time t equal to 0, before we have any kind of rotational motion, we have 2 sets of axes coinciding with each other. So, we have x, y, z, which are the body set of axis attached to the body, and we have x prime, y prime and z prime, which are the space set of axis, right. Now, we start rotating Okay. Now we start the movement. Firstly, what do we do? And let us assume that we have some kind, let us just draw a laminar object just to give you a better understanding of the thing. So, let us say this is the object for which we have two sets of axes coinciding at time t equal to 0, right. Now, as we move on, the first rotation we get, we call it the phi rotation. What is this phi rotation? So, let us say the phi rotation is about, and please understand this, x prime, y prime and z prime, these are fixed frames. So, whatever we do, these are not moving. X, y, z, when we are moving the object, the moving the object, this x, y, z axis will be moving. So, first is rotation in anti-clockwise direction by an angle phi around this z axis. Okay. It does not matter whether it is a body z or space z, because at this point of time both are same. So, now how does this new set of axis will look like? So, let us assume, okay, let us draw the first, at first this is the x prime, y prime, z prime. For new set of axis, it is okay. So, this is phi, this is phi, right. Now, we will call this set of axis as what should I do? Okay, let us call it capital X, yeah, just a nomenclature, capital Y and capital Z. At capital Z and small z prime, they are coinciding at present. So, the object which we were discussing will also rotate slightly in the xy plane. Okay, so, it is the rotation of this object. Next, we rotate this object around this new x axis, okay, by an angle theta. Okay. So, if I now try to draw this, what is the best way of drawing it? Okay, let us try this out and see. So, we have this object, let us say. Now, we are moving it, tilting it by angle theta. So, let us say this is the new set of so it was the initial position, and once again we draw okay. Okay, so this is a bad drawing. Okay, let's not use this. There is a reason for it. I'll tell you in a moment. So actually, a good drawing will be this. Hopefully, this is my object initially. So this is my x, right? Okay. So I'll explain in a moment what it is. Just be patient, right? Okay. So once again we have z, x, y, x prime, y prime, z prime. Now let us use this color. Now this is my y, this is my x, and this is my z. So initially we rotated this axis system by in a so all these rotations are in anti-clockwise direction. Okay. So the rotation direction was this. Okay. And next we rotated it by theta, which the direction of rotation is this along this, so forget about this, along this new x axis. Okay. So, now what happens in this new set, which we call x prime, capital X prime, capital Y prime, capital Z prime, right. Okay. And this capital X prime and capital X coincides with each other, because capital X is the after first phi rotation. Okay. Now, because the rotation is around this axis remains invariant, right. So, we have this new set. And lastly, so this is theta rotation, and lastly we will have something called the psi rotation. What is the psi rotations? Psi rotation is about this new capital Z prime axis. So, new Z axis after the first and second rotation, okay, by an angle psi, once again in the anticlockwise direction. So, how will that be? Let us try to draw this first. So, this is my initial position of the object, this is just for reference. This was my second, yeah, so this was my position after two rotations, capital X prime, and now I rotate it by another psi around this Z axis, which is capital Z prime. Now, it will go to, so this is capital Z prime, it will go to small z, and my new y will be small y and x will be small x, right. And original position x prime, y prime, z prime, right. So, we have one theta rotation, phi rotation, which is around the initial z axis where body and space, I mean both coincides. Then the second rotation is around the new x axis, which is by an angle theta in the anticlockwise direction, and the last psi rotation is around new y axis, new z axis after the second rotation by an angle which is given here. So, this is the angle psi. Okay. So, phi, theta and psi, these three are my, so this is phi, this is theta and this is psi. So, these three, please remember that this is only one definition of Euler angles. Okay. So, Euler angles can be expressed, so this is a z x z definition, it is called z x z because the first rotation is around z, second is around x and third is once again around z. So, we can likewise we can have x y x, we can have z y z, z y z, yeah. So, all these are possible combinations we can have. So, we are but we for our discussion we will just stick to this. You can check in Wikipedia, there is a very nice discussion like in many other articles in Wikipedia, where the alternative definitions of Euler angles are described. Now we have the angles, what to do with it? We have defined three sets of angles, and if you pay attention, the first set of axis was x, y, z. Okay, I should not write this as my, so first set of axis let us say was x prime, y prime, z prime, let us not write this. Okay. So, and it was coinciding, two sets of axes were coinciding. So, I will level them both as this. Next set of axis is x, capital X, capital Y, capital Z. Third, we have capital X prime, capital Y prime, capital Z prime, and last we have small x, small y, small z. So, the flow of movement, if we just go by the notation, it is x prime, y prime, z prime. Just to summarize, we have phi, then we go to capital X, capital Y, capital Z, theta, we have capital X prime, capital Y prime, capital Z prime, okay, phi, theta, and then we have psi, we go to x, y and z. So, this is my first space set of axes, and it remains unaltered, and this is my final body set of axes which is attached to the rigid body. So, this three angles, essentially the combination of these three rotations can describe any arbitrary rotation around of rigid body. So, these are the most general case we can have in terms of rigid body rotation. Okay. These are proofs. So, there are proofs which are more mathematical in nature and which we are avoiding altogether, but we will do some mathematics. Of course, we have to do some mathematics. So, let us look at it in a slightly different way. Initially, we have I prime, j prime and k prime as our sets of coordinate. Then after the first phi rotation, let us say we have I, capital J and capital K as our 3 direction vectors. Then let us say we have capital I prime, capital J prime and capital K prime for the next theta rotation, and for the final psi rotation we have small x or small I prime, small I, small j, small k. Okay. So, and as I said already, each of these coordinate transformation can be expressed in terms of a rotation. I mean, these are all rotations. So, essentially we can link up these two sets of coordinate by some rotational transformation matrix. So, this rotational transformation matrix, if I write it out, so first we have to start with R phi, which will be, please remember that phi rotation is again against around z direction. So, we have cos phi, sin phi 0, minus sin phi, cos phi 0, 0, 0, 1. So, similarly R theta, which is again against an x axis, about an x axis. So, x axis remains invariant, and we have cos theta, sin theta, minus sin theta, sin theta. See, you have 0, 0 and 0, 0 here and 1 in the diagonal term. That means, this direction is invariant. So, x for the second rotation x is invariant, and for the third rotation R psi, which is once again is around a z axis. So, we will have this and cos psi, sin psi, minus sin psi, cos psi, and everywhere it is anti-clockwise rotation, anti-clockwise, and please remember these are passive rotations, because actually we are assuming that the, okay, can we call it passive? Yeah, actually we can call it passive rotations, right, because the coordinate system itself is moving, right. So, anyway, now what to do with these matrices? Thing is, we can actually use these matrices to track down the change in this coordinate. So, essentially if we want to write a vector, so let us say that our final target is we want to decompose omega into in terms of this final sets of system, because we always try to end up by this set of rotation in an axis system, which is not only the body frame, but also which is chosen to be the axis, the what you call the inertial axis system. So, in this inertial axis system, omega will be decomposed into omega 1 I cap plus omega 2 j cap plus omega 3 k cap, that we know already. And this I, j and k, they are continuously changing, because this rotation, see these values of theta, phi, theta and psi, if we take combinations of phi, theta and psi, we will get different values of I and j and k corresponding to the static frame. This is not changing, this is static. These two things, they are static, okay, there is a space, and these final things they are moving. Now, using this rotation matrices systematically, we can write out I, j and k, these 3 unit vectors in terms of I prime, j prime and k prime, right. So, we can do that. This is what, well, actually we do it in the other way around, but we can do that. What we can do is we can actually start in a slightly different manner. We can start by writing, you know, we can start, just give me a second, I will right. So, we can do that. Also what we can do is we can write I prime, j prime and k prime in terms of I, j and k. So, finally, what we are trying to do is we are trying to express omega 1, omega 2 and omega 3 in terms of phi, theta and psi. Now, if we can do that, okay, so forget about this. This is strictly is not needed at this point to understand. We probably it is what I said is not correct. Okay, let us forget that. So, let us start once again from here. We have omega 1, omega 2 and omega 3, where I, j and k is expressed in the body set of axes, which are continuously rotating with the rigid body. But if we can write omega 1, omega 2 and omega 3 in terms of phi, theta and psi, which is in some sense associated with the space set of axes by this sets of rotation, then in principle, if we integrate these equations for omega 1, omega 2 and omega 3 and get the expressions of omega 1, omega 2, omega 3 in terms of these 3 angles, what we can essentially say is we can essentially comment on the nature of the motion, because all these angles they are somehow connected with the space set of axes. We will take an example of symmetric top under heavy symmetric top and we will see how it happens. Now, what can be done is, okay, what can be done is we can write this equation in a slightly alternative form. See, we are finally aiming to write in terms of omega 1 I cap, omega 2 j cap and omega 3 k cap. But what we can begin with, we can start writing the angular velocity corresponding to this rotation to be omega phi, which is nothing but phi dot. Similarly, we can write the angular velocity with respect to this as omega theta, which is equal to theta dot, and here we can write omega psi, which is equal to psi dot. Now, if we write omega in this in terms of phi theta, omega phi, omega theta and omega psi, we can write it as omega equal to omega phi capital omega phi small k cap plus omega phi theta, right, omega theta capital I cap plus omega psi capital K cap, right, which is nothing but phi dot capital K cap or small k cap plus theta dot capital I cap plus psi dot capital K cap, right. Now, this we have this transformation relations, and using these transformation relations we can essentially express this small k cap in terms of, okay, so what I said here actually, which is scratched, what I scratched out, essentially this small I mean x prime, y prime, z prime or small I cap, small j cap, small k cap can also be expressed in terms of I, j and k. Okay. So, similarly this capital I can also be expressed in terms of I, j and k, and capital K cap can also be expressed in terms of I, j and k, which are the final body sets of coordinate. Okay. So, once we do that, we can it can be shown. Please check theoretical mechanics by Spiegel for a detailed detailed derivation. We are not doing it. It's just it's the same thing. We have to just do systematic matrix multiplications, and finally we will end up in a relation which is omega 1 phi dot sin theta sin psi plus theta dot cos psi. Omega 2 is equal to phi dot sin theta cos psi minus theta dot sin psi, and omega 3 is equal to phi dot cos theta plus psi dot. So, these three are the sets of Euler's equation. These three are the expression which correlates omega 1, omega 2, omega 3 expressed once again in body frame. But now we have three coordinates to track the changes in omega 1, omega 2 and omega 3. And these three changes are these three coordinates are somehow associated with a rotation around body set of axis, space set of axis. So, this can be used in order to in order to determine the motion of certain object. So, we will take the example of heavy symmetric top and figure out how to use these three sets of equation in order to express the motion of this top. Now, what is heavy symmetric top? You must have seen, you must have played with child's top, right. So, heavy symmetric top, one of the examples of heavy symmetric top could be a child's top. Why it is called heavy? Because so far we have discussed symmetric top in torque free condition. Now, when a child's top rotates on the table on a plane, it also comes under the action of influence of gravity, and that gravity is, let us say, if this is the axis of the top, which is never, which in a very special case can stay just upright like this, but even then there is a gravitational pull which is acting along the line of this torque, okay, axis of this torque. But moment, this is a very special case, we will see that later, but in general the axis is slightly tilted, and the torque, we know that the top is, sometimes the axis is also moving like this and going up and down. We have seen that if we have played with this child's top, and moment it is slightly tilted from this vertical position, there is a torque which is acting due to its weight. Okay, and we will see that component of this torque will be always along the body x axis. We will see all this. So, let us try to draw this situation. Let us take child's top as a case of heavy symmetric top and try to write the equations of it. So, we have this top, okay, which is moving. Let us take, this is the axis. Okay. Let us take the origin here. So, I set my z prime axis, y prime axis and x prime axis like this. Okay. Now, in order to write the equation, we can also take this omega 1, omega 2 and omega 3 and start from here. But what is feasible, because we are using, we have to do lots of mathematics in the understanding of heavy symmetric top. It is better if we take a coordinate system which is, of course, we have to take a coordinate system which is spinning along with the top. So, let us say this is my phi, okay, and this angle is theta. See what happens if the top rotates around its direction. So this actually is the first Euler's angle, this actually is the second Euler angle, and about the third Euler angle, we can just take we can just assume that the torque is, the top is spinning with an angular velocity of psi dot. So, what we are going to do is, instead of using these equations directly, we will be working in a frame in which psi equal to 0. Okay. So, once we put psi equal to 0, and so that means the coordinate, we are not considering the third Euler angle directly into this system. Why we do that, we will see in a moment, because this will greatly simplify our calculations. But please understand, by doing this, we are not, not losing any generality of the problem. See, what we need to understand, that there are three types of motion possible in a heavy symmetric top. So, first of all, why it is called heavy? Because let us assume that the center of mass is somewhere in this axis by the symmetry of the problem, right. Now, this center of mass has, so we have seen that for a system of particle, we can assume that all the forces are acting directly at the center of mass. So, the moment so the total moment of this force, which is the torque, this is acting in, the force is acting in this particular direction, and if this height is h, this length from here to here, then we can calculate what is the exact value of the torque. Now, there could be three different types of motion here. One is the spin motion of the top, if it is spinning. The second motion is the axis can actually go up and down with respect to the fixed z axis, that is the space z axis. So, that is very nicely nicely taken into account by the change in theta. Okay. And it can also, this axis can also rotate. So, let us say I have two pens in my hand. Let us assume that this one is the vertical direction, that is the fixed axis, and this is the axis of the top. Okay. So, the top axis can go something like up and down, which is taken by this particular angle theta. Also, it can rotate, it makes a precision motion around this axis, either like this or like this, and this precision is taken care by this particular angle phi. Okay. And there is a third motion, which is the spin, which is taken care by psi dot. We can just put a psi dot for the spin part, right. So, what we can do is, we can take this equation, we can put psi equal to 0, and then we write omega 1 equal to, if we put psi equal to 0, this one equal to 1, this is becomes 0. So, we have theta dot omega 2 is equal to minus theta dot, oh sorry, this will survive, because we have phi dot sin theta minus, oh this will not survive, and omega 3 will be phi dot cos theta plus psi dot. So, these will be my values of omega 1, omega 2 and omega 3. So, we will start from here in the next lecture. Okay. So, we will continue our discussion, and right now we have to stop here because of time limitation. We will continue very soon with the next lecture.